second degree equation. So this one here 0 coefficient, here x coefficient is 0, and here constant is 0. So this is our p1, p2 and p3. So now let us write in this form. 2, we have need find this k1, k2 and k3, all value of k1, k2 and k3. So we write in this form, means this p1, p2, p3, that means p equal to k1 p1 plus k2 p2 plus k3 p3. Now multiply this k1 k2 inside bracket, so we get this one constant term k1 plus k2. Now x coefficient, so k1 plus k2 is x coefficient and k2 plus k3 is x square coefficient. Now compare both sides. So here 2 is constant term, so k1 plus k2 is 2. Now x coefficient is -1, so similarly here x coefficient is k1 plus k3, so k1 plus k3 equal to -1, and here x square coefficient is k2 plus k3, and here x square coefficient is 1, so this equal to 1. Now solving this equation, that means here by apply directly simple method by k1 equal to 2 minus k2 and substitute in any one, and then similarly any, and then find solution, last solution k1 k2 k3. Or another method is Gauss elimination or Gauss Jordan, any method. So here we directly write, because this is a simple equation, so directly write this solution k1 equal to 0, k2 equal to 2 and k3 equal to -1. This is a solution. Therefore this our last solution means coordinate vector ps, that means this p coordinate vector is this one up on set S, so equal to 0 to -1. 0 is k1, 2 is k2 and k3 is -1. This is a coordinate vector of the given p. Now question number 3c1, find the two vector in R3, means find R3 vectors, two vector, and its property means Euclidean norm is 1. That means if we consider any two vector, its Euclidean norm is 1, whose inner product, that means inner product of any vector, that means here given that vector is -3 1 is 0, that means inner product is 0. So like we consider here let u equal to u1 u2, this is our first vector, and v equal to v1 v2. Now given that norm u, here we have given that means this vector norm, that means like this definition of norm u equal to square root of first element square plus second element square, that means sum of square of all elements, this and its square root, it's a norm. This is a definition of norm. So this equal to given that 1. Similarly norm v equal to v1 square plus v2 square square root, so it's also given that 1. And second is given the inner product is 0. Now here given that R3, that means it's Euclidean inner product space. So in Euclidean inner product space, inner product is dot product. So dot product is u1 -3 plus u2 -1 equal to 0. So we write here -3 into u1 plus u2 into 1, so u2 equal to 0. This so simplify, so u2 equal to this minus is take right hand side, so it's convert in 3u1. Okay, similarly v1 v2 dot -3 1 0, that means dot product, because inner product is dot product in R3 because Euclidean inner product space. So v1 v2 -3 1 equal to 0, so -3 into v1 plus 1 into v2, so 0. So v2 equal to 3 1. Now here this numbering 1 2 3 and 4, using the 1 2 3 4 we solve and then find u1 u2 v1 v2 like this one. So from 1 2 3 and 4, and therefore square root of u1 square plus 9u1 square equal to 1, because in last from last equation number 3, this equation number 3 is u1 u2 equal to 3u1, so e square is 9u1, and from 1 is u1 square plus u2 square, so 9 first and third, that means this first and this third from 1 and 3, so this is square root equal to 1. Therefore square root of 10 u1 square equal to 1. Now take u1 is common, so we get u1 equal to square root of 10 equal to 1 from this last one. So now therefore u1 equal to multiply by 1 upon 10 in both sides. So root 10 1 upon root 10, so 1 upon root 10 is cancelled, so equal to 1 upon root 10, so u1 is 1 upon root 10. Now substitute in equation number 3, so we get u2 equal to 3 upon root 10. This is a u1 and u2. That means here one vector is u1 is 1 upon root 2, u2 is 3 upon root 2. That means u is 1 upon root 2, 3 upon root 2. Similarly for v1 v2, so here in number 4 equation 9 3v1, that means v2 equal to 3v1, so its square is 9v1 square. Adding this both, so we get 10v1 square. Now v1 is common, so we get v1 into root 10 equal to 1. Similarly in last this one, multiply by 1 upon root 10, so v1 equal to 1 upon root 10, and then substitute in number 4, so v2 equal to 3 upon root 10. Hence the last solution is u is our this number 1 vector is 1 upon root 2 and 3 upon root 2, and v is 1 upon root 2 and 3 upon root 2. Now next is if v1 v2 v3 is and vr are pairwise orthogonal vector in Rn. So v1 v2 v3 and vr are pairwise orthogonal vector in Rn. That means v1 v2 its dot product is 0, v2 v3 dot product is 0, v3 v4 dot product 0. Similarly all means pairwise orthogonal, and similarly v1 v3 dot product is also 0, means all pair is 0 except v1 and v1 means dot product is non-zero. Now yeah, pairwise orthogonal vector in Rn. Then this one, prove that this means we have answer is this, means this norm square equal to this one. Next, so solution is like this one. So here given that this left hand side our, now by using inner product, so we write in this form v1 v2 v3 comma v1. Similarly this one, this is definition of norm in inner products. Now we also using this, so we write in this form v1, and then here this is take right second by using inner product definition, and this is as it is v1 v2 v3 plus vr. Similarly this one. Okay. Now once again apply this property, so v1 v1 and then here plus v1 and this v2 and so on. Here v2, similarly this one. Now here this is orthogonal, so another v1 and v1 it's norm v1, but if v2 v1 and v2 then 0, but here given the reason because all vector is pairwise orthogonal, so v1 vi and vj where I and j not equal to 0 is 0, but if I and j both are same, then we can write this equal to norm v1 square. Similarly v2 v2 then square, this is square. Similarly all. So this is the last right hand side of the our example. This is last solution. Okay. Now next question number 4a. Let R3 have a Euclidean inner product. That means R3 is our vector space. So Euclidean inner product is given using Gram-Schmidt process to transform the basis, means this is our basis, and here given that this is into orthonormal basis. Means this Gram-Schmidt process, it convert in any vector in orthonormal basis. That means its norm is 1. So like this one solution here given that u1 is this, u2 u3 means in example. So but now by Gram-Schmidt process is first take this u1 is any vector, consider here y1, so y1 equal to u1 and this 1 0 0 and its norm is 1. Here look at this is norm is 1. Now u2 is take y2 and minus u2 dot y1, this y1, this here r3, so here dot product because r3 is Euclidean inner product, so u2 dot y1. If here consider r3 is not a here sorry if it not a r3, so r3 r2, that means Euclidean inner product, then apply inner product space. So u2 dot y1 and this into y1 means this is a vector product, not inner product, and this is norm y1 square. Now substitute all vector or all value. So u2 is this 3 7 minus 2, and u2 is also the same. Y1 is already find that, so y1 is 1 0 0 and norm y1 is 1 1 0 0 is our y1. So we get this is answer dot product means 3 0 0 1 0 divide by 1, then 3 divide by 1 multiply inside, so we get 3. Now this is 3 7 minus 2 3 3 0 0 adding this, so this is norm y2 equal to this one. Now next y3 equal to definition is this one, u3 that in minus this one minus this process, Gram-Schmidt process. So u3 is 0 for 1, u3 substitute all value, so u3 vector value or norm value. Okay, so this is answer equal to multiply, so a dot product, so we get 0 0 into 4, and then this is 0, so all value is 0. Similarly this solution of this one, okay, and 0 for 1, so we get like this one 0 for 1 minus 26 by 53, and this one. Now this is 0 for minus this vector is solution of this vector and this scalar, so this is the answer, and then subtract from this, so we get last answer, and its norm is this one. Now require orthonormal bases are, now 1 0 0 divide by its norm, so we get 1 0 0. Now 0 into this last one, this 0 7 minus 2 divide by its norm root 53, so we get orthonormal basis, this orthonormal basis. And next this vector 0 33 30 53 105 53 divide by this one, so we get this answer. So this is our last solution. If we find norm of this all vector, then we get answer is always 1. Okay, then this is last solution. Now question number 4b1, find the least square solution of the linear system ax equal to b given by this linear system, and find the orthogonal projection of b on the column space of A, means find orthogonal projection of B on column space of A. So now we let continue. So here A equal to this coefficient matrix A is this coefficient matrix 1 minus 1 3 2 minus 2 4 of this system, and 4 1 3 is a constant column matrix. A is linear independent column vectors, means A is linear independent. Their unique least square solution, means if this not independent, then not a unique solution. So here this is independent, that means not depend on each other, so it's called linear independent. Now we have A transform, we find A transform into A. So here this A transform is means this column is converting row, and this column is converting second row. So here 1 3 minus 2 and 1 minus 1 2 4. So and this A is same as, now multiply, so this into this row, so we get 14, and then this column into first row, so we get minus 3, and similarly 1 3 minus 2 multiply this element corresponding element minus 1 1, similarly, so we get minus 3. Now and second last column is multiplied second row, so we get 21. This answer of A transform A, 14 minus 3 minus 3 and 21. Now second operation, we have need this solution, so A transform into B, that means transform of this, that means this into this one, so we get 1 and 10, that means column matrix, because here this second matrix is in one column, so we get answer in column. Next So the normal system like this one, we have need this solution. So A transform A into X, A transform into B is, now this answer is last slide, and this is the same. Now this is a system of equation. If we multiply this column matrix in this matrix, so 14x1 minus 3x2 equal to 1 and minus 3x1 plus 21x2 equal to 10. So it's a system of equation. Two unknown here, x1 x2 are two unknown, and then solve by using Gauss elimination. Here write only elimination, but it's called Gauss elimination method. So that means it's convert this matrix, augmented matrix, this is our augmented matrix in row echelon form. That means find leading one and then lower value all element in column is 0. So now R1 into 1 upon 40, that means first row multiply by 1 upon 40. So we get this answer, and then using this one leading one, this is our leading one in first leading one. Now using this one this minus 3 converting 0 form. So 3 into 1, so we get 3 plus minus 3, so we get 0. Similarly in all corresponding element in all column, so R12 into 3, so we get this answer. Next, so 1 minus 3 14, 1 14 is R12 into 3, so we get this means using this R12 into 3. Okay, this is a repeat another, so it's cancelled now directly this matrix. Now next leading one is here 285 divided by 14, because next leading one, this last leading one, next leading one in next row and next column, that means this is next column and this next row, that means here now, and this is non-zero, so we get last leading one in here. So multiply 14 into 14 divided by 285 with here, this convert in 1. Similarly multiply with here, so 14 divided by 185 285, not 185, this is typing mistake. So we get 1 divided by 285, and then apply by back substitution rule. So here x2 equal to this 143 divided by 285, and using this value and this first row, that means x1 minus 314 x2 equal to 1 upon 40, and substitute this x2 in this, so we get answer is x1 equal to 17 by 95, this x1 and x2. Now